distribution. So we have the standard normal distribution and then using the normal distribution to find various probabilities. By the end of this chapter, you should be able to recognize the normal probability distribution and apply it appropriately, recognize the standard normal probability distribution and apply it appropriately, and compare normal probabilities by converting to the standard normal distribution. The normal, which is a continuous distribution, is the most important of all the distributions. The graph is bell-shaped. You see the bell curve in almost all disciplines. Some of these include psychology, business, economics, the sciences, nursing, and of course, mathematics. Some of your instructors may use the normal distribution to help determine your grade. Most IQ scores are normally distributed. Often real estate prices fit a normal distribution. The normal distribution is extremely important, but it cannot be applied to everything in the real world. In this chapter, you will study the normal distribution, the standard normal distribution, and applications associated with them. The normal distribution uses the mean and standard deviation as parameters. If X is a quantity to be measured that has a normal distribution with a mean, which we use the Greek letter mu, and a standard deviation, which we use the Greek letter lowercase sigma, we designate this by writing that capital X is a random variable such that it fits a normal distribution with a mean of mu and a standard deviation of sigma. The cumulative distribution function is that find the probability that X is less than some value. It's either calculated by computer, a calculator, or it's looked up in a table. This notation will be super important, being able to read it and being able to say that X fits a random variable, or X is a random variable that fits a normal distribution with a specific mean or standard deviation. The curve is symmetrical about a vertical line drawn through the mean. So in theory, the mean is the same as the median. So our mean would be in the middle there. And our median would also be there. As the notation indicates, the normal distribution depends only on the mean and the standard deviation. Since the area under the curve must equal 1, a change in the standard deviation causes a change in the shape of the curve. The curve becomes either fatter or skinnier depending on the standard deviation. A change in the mean would shift the graph to the left or the right. This means that there are an infinite number of normal probability distributions. However, one special one is called the standard normal distribution. So the standard normal distribution is a normal distribution of standardized values called z-score. A z-score is measured in units of the standard deviation. So for example, if the mean of a normal distribution is 5 and the standard deviation is 2, the value 11 is 3 standard deviations above the mean, so the z-score would be 3. The z-score is found by taking the value minus the mean divided by the standard deviation. If we apply that then to a normal curve, the standard normal distribution is a normal curve with a mean of 0 and a standard deviation of 1. So if you look here, this would be our standard normal. So it's a normal distribution with a mean of 0, so that's in the middle, and a standard deviation of 1. So a positive z-score, positive 1, 2, 3, negative 1, negative 2, negative 3 z-scores. If X is a normally distributed random variable, so this would be our notation saying X is a randomly distributed variable with a normal distribution with a mean and standard deviation, then the z-score is found by taking the data value minus the mean divided by the standard deviation. The z-score tells you how many standard deviations the X value is above or below the mean or to the right or left of the mean. Values that are larger than the mean have positive z-scores. Values that are smaller than the mean have negative z-scores. If a value is equal to the mean, it has a z-score of 0. The z-score allows us to compare data that are scaled differently. So for example, suppose that x is a random variable that is normally distributed with a mean of 5 and a standard deviation of 6. Suppose that we have the value x is 17. Thus that means that 17 minus 5 divided by 6 is 2, so the z-score is 2. So 17 is 2 standard deviations above the mean of 5. Now suppose that x equals 1. If we take 1 minus 5 and divide it by 6, we get a z-score of negative 0.67, so that means that 1 is 0.67 standard deviations below the mean. So again, just remember that when z is positive, the x value is above or to the right of the mean. When z is negative, x is to the left or below the mean. The further away from 0 the z-score is, the further away from the mean that value is. The empirical rule, which I believe we've already talked about, is also known as the 68, 95, 99.7 rule. About 68% of the data values lie between 1 standard deviation of the mean. So in our picture here, 1 standard deviation below to 1 standard deviation above the mean is 68% of the data. About 95% of the data is either above or below the mean by 2 standard deviations. So either it's going above the mean by 2 standard deviations or below the mean. And within 3 standard deviations of the mean is 99.7% of the data. Notice that almost all x values lie within 3 standard deviations of the mean. In 2012, 1,664,479 students took the SAT exam. The distribution of the scores in the verbal section of the SAT had a mean of 496 and a standard deviation of 114. Let x, the random variable x, be an SAT exam verbal score in 2012. Then x, the random variable x, fits a normal distribution with a mean of 496 and a standard deviation of 114. Find the z-scores for each of those data values, interpret the z-scores, and then what can we say about those data values? So let's start with the first data value of 325. To find the z-score, we take 325 minus the mean, which the mean was 496, and we divide that by the standard deviation of 114. So we get a z-score of negative 1.5. What this means is 325 is 1.5 standard deviations below the mean. The second value that it wants us to do this with is a score of 366.21. Again, to find the z-score, we take that number, the data value, minus the mean, divided by the standard deviation. So we get a z-score of negative 1.14. So 366.21 is 1.14 standard deviations below the mean. So what that means is student 2 was closer to the mean because they were only 1.14 standard deviations below the mean, whereas student 1 was 1.5 standard deviations below the mean. That also means that student 2's score was better. Now, obviously, we would want that score to be above the mean. Now, keep in mind, what does it represent? Like, if we're talking about golf scores, you want a lower golf score, so you want to be below the mean. But since we're talking about scoring on a test, we want a high score, so we want to be above the mean. Okay, these are some added examples from questions on the homework over the past few years. This is a standard normal distribution. This is representing a picture that the probability that a z-score is less than 1.3. A z-score of 1.3 would be here on my x-axis, and then the probability that the z-score is less than that would be all of this shaded region would be less than at 1.3. Less than or equal to or less than does not matter in this case. That's only with the binomial distribution. It does not matter with the normal distribution. Okay, so this would be a picture representing the probability that z is greater than or equal to a z-score of negative 0.53. So negative 0.53 would be about here. Greater than would be this area to the right of that. All right, so shade the probability that z is less than negative 1.2. A z-score of negative 1.2 would be just to the left of negative 1. And then to the z less than that would be all of this area here. Remember that probability is that shaded area under the curve. Okay, and then draw a picture representing the probability that z is greater than 2.1. First, I would want to find a z-score of 2.1. So that z-score is 2.1 standard deviations above the mean. Our z-scores on the standard normal curve are the same as the x-coordinates, and greater than would be this area here. All right, now I'm going to show you how to find these actual probabilities using a TI-84 graphing calculator. So find the probability that a z-score is less than 0.78, where z is the standard normal variable. Standard normal means that the mean is 0 and the standard deviation is 1. That's what the standard normal variable means. Always. You can find the area under any normal curve by, on your graphing calculator, hitting second, and then the vars button or variable button has that blue distribution written above it. And then we're going to do normal CDF. That is the cumulative distribution under a value. All right, so we're going to find the probability that z is less than 0.78 using our graphing calculator. So second, distribution, which is this variable button. And we are using a normal curve, so we're going to use normal CDF because it's the cumulative area. And if your lower value is not given to you, we're going to think logically here. This is just the standard normal curve, so we want a ridiculously low value. So the default is like negative 1 E99. If you need a really high value, you use 1 E99. Now, in the future, if you are ever talking about like test scores, you can't have a negative test score, so your lower would be 0, or your upper would be 100 because you can't go above 100 on a test score, or whatever it is. So our lower bound is negative 1 E99. The highest that we want the z-score to be is 0.78 because we're finding the probability that z is less than 0.78. Since it's the standard normal, our mean is 0 and our standard deviation is 1. So I'm going to paste that, I'm going to hit enter, and we get a probability of 0.7823. Just to help illustrate a picture. Remember, our standard normal curve has 0 in the middle. 1, 2. So I want the probability that z is greater than 1.32. So this time our lower is 1.32 because that's where our shading is going to start. Our upper is going to be some ridiculously high number like 1e99. So that's 1 times 10 to the 99th power. So again, second distribution, normal CDF. My lower is 1.32. My upper is 1e, which do not use this green E here. We want this blue EE above the comma. So second E99. Mean and standard deviation stay the same for the standard normal curve. So I'm going to paste that. I'm going to hit enter and we get 0.0934. Okay, and then the last one that was on the notes was that what's the probability that z is in between two values? So if I'm using my graphing calculator, I'm doing the normal CDF. I want z to be in between negative 1.22 and 2.45. So that's my lower, my upper bound. My mean and standard deviation stay the same because it's the standard normal curve. So my probability for that is 0.8816. So we just did, our lower was negative 1.22, upper on a picture, it'd be the shading in between them. If that helps you to see that picture. Find the area under the standard normal curve to the left of a z-score of negative 2.31. So this is asking you to find, here's our standard normal. Standard normal means a mean of 0 and a standard deviation of 1. So a z-score of negative 2.31 in the area under the curve to the left of that. So it's asking you to find the probability, which is the same as the area under the curve. So it's what we were just doing. So we're going to still use that normal CDF function on our calculator. Our lower is going to be negative 1e99. I always just think of that as negative infinity. Our upper is negative 2.31. And then I'm going to go ahead and draw the picture of B and talk about the lower and upper of that one as well before going to the graphing calculator for how to type them in. So find the area under the standard normal curve to the left of a z-score of 1.31. So on my standard normal, 0 is in the middle. 1.31 would be over here, and I want the area to the left of that. So that shading starts at negative infinity. So our lower is negative 1e99. Our upper is the shading stops at that z-score of 1.31. So again, to get to that normal CDF, second distribution, which is that VARS normal CDF, and I can put my lower as negative 1e, which is second, and then it's that comma button. That's how I get that negative infinity. My first upper was negative 2.31. And my mean and standard deviation are staying the same because it's the standard normal curve. So that probability is 0.0104. And then you would follow the same steps for that other value. Just change the upper to 1.31. Find the area under the standard normal curve to the right of a z-score of negative 2.31. So standard normal, still with a mean of 0, standard deviation of 1. So a z-score of negative 2.31 would be below the mean of 0. This time we want the area to the right of that. So this time our lower is negative 1.31, or I'm sorry, 2.31. And our upper goes all the way to positive infinity. So I use 1e99 for that. So same thing, my picture for B. Zero's in the middle, a z-score of 1.31, and the area to the right. Your lower would be that 1.31, and your upper positive infinity, so 1e99. And then you would still just use that second distribution. Normal CDF, the cumulative area, and change your upper and lower to match these pictures. Okay, so now find the z-score such that the area to the left of it is blah, blah, blah. When you are given the area, we use the inverse norm function. And that's in that same area of the second distribution, and we're going to go to inverse norm. So this is saying find the z-score such that the area to the left of that z-score is 0.41. So something I want you to think about is the shading is to the left. So when we do inverse norm, it's going to ask for a tail location. Our tail is to the left because we're looking for this value and the shading is going to the left of it. So on my calculator, second distribution still, and inverse norm is that third one. Our area was 0.41. We still have a mean and standard deviation of 0 and 1. Our tail was to the left of that. So that z-score that corresponds with it is negative 0.228. Okay, this time we're going to find the z-score such that the area to the right of the given, or the area to the right of the z-score is given to it. So this time, our z value is going to be to the right of the mean, because that mean should be 50%, right? So this area is 0.41. This time, we're looking for a z-score and the shading goes to the right of it, so that's going to change our tail and make it go to the right on that inverse norm menu. So second distribution, inverse norm is number 3. Our area is 0.41. Mean and standard deviation are the same, but this time our tail is to the right. So we get a z-score of 0.228, of positive 0.228. All right, last thing for 6.1. Find the given percentile of the standard normal distribution. Standard normal means that the mean is 0, standard deviation is 1. Remember that percentile is always the area to the left, the probability that the data values are to the left of it. Okay, so this K value, that's your percentile. So we're going to do it the same way as the previous slide. It's asking for the same computation, it's just asking it in a different way. So if we are looking for the 9th percentile, that means that 9% of the data values are less than or equal to whatever that is. So our area is going to be 0.09. We are using the inverse norm feature. The tail for percentile is always to the left because it's the percentage of data values that are less than or equal to it. And our mean and standard deviation are still 0 and 1. Before I go to my graphing calculator, I'm going to do B as well. Our area on B, if we're looking for the 71st percentile, would be 0.71. 71% of the data are less than or equal to it. Your tail is still to the left, always for percentiles. So if I go to inverse or second distribution, inverse norm, I can do that 0.09 area. Your tail is always to the left for percentiles. So the 9th percentile of the standard normal curve is negative 1.341. And then you would just do the same thing with the area of 0.71 to do B. All right, so now 6.2 is about using the normal distribution when it's not necessarily the standard normal curve. So remember that the shaded area under the curve represents the probability that x, in this case, is less than or equal to some value. We've been using the normal CDF to do this. The area to the left can be found, or to the right, I'm sorry, can be found as 1 minus the area to the left, or as I've already shown you on that normal CDF, you can switch your tail so that way you don't have to remember that 1 minus thing. You can just do the tail that matches your drawing. I do think that drawing a picture is very helpful with these types of problems. And then the last thing, notice that if x is less than some value or x is less than or equal to some value, that's the same for continuous distributions. Binomial is not the same, continuous is. So normal is a continuous distribution, whereas binomial is discrete because you're counting. So less than or equal to is the same as less than. All right, so the final exam scores in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. Find the probability that a randomly selected student scored more than 65 on the exam. So this would be a picture. A normal distribution is a bell curve. Your mean goes in the middle. Okay, so that's why 63 is in the middle. And then a standard deviation of 5 typically means that the tick marks we would put on the x-axis, we'd be counting by 5. So we'd go up to 68, up to 73, and then down to 58, and so on and so forth. So this picture is already drawn for you, and it's already given you the probability. You would do this on your graphing calculator the same way as we've been doing with that second distribution normal CDF. You just would change your mean and standard deviation to match whatever your values are, because this is no longer the standard normal curve. This is just any normal distribution with its own mean and standard deviation. In this case, for this problem, our lower bound would be 65. Right, because that's where our shading starts, and then it goes up to infinity. So 1E99 would be our upper bound. And then you would put in your mean and standard deviation. Okay, so using those same numbers, draw a graph for the probability that a randomly selected student scored less than 85. So if I have my curve, our mean was 63. So that's going to go in the middle. 85, and we want the probability that a student scored less than that. The lowest value that a student can score is 0. Test scores cannot go negative. If we could go negative, we would use that -1 E99. But the lower bound is 0 since the test scores cannot go negative. Our upper bound, our shading stops at 85. Our mean is 63 and the standard deviation is 5. That was given to us in the problem. So if I go to second distribution and we want normal CDF, that second one, our lower bound is 0, our upper is 85, our mean is 63 and our standard deviation is 5. So I do have to change those to match the distribution for this data. So we get 0.9999999, which means basically 1 or 100%. So the probability that one student scores less than 85 is approximately 100%. Find the 90th percentile, meaning that find the score that has 90% of the scores below that value or 10% of the scores above. So here's what our picture would look like. What is this value such that 90% of the scores are below it, or an area of 0.90? So remember, when we're given the area, we're going to use that inverse norm feature. Our area is 0.90. And then we still have our mean and standard deviation given to us in the problem. This is a tail that's to the left because we're looking for this value and the shadings to the left of it. So second distribution, inverse norm, so number 3. Our area was 0.90 for the 90th percentile. Mean and standard deviation given to us in the problem were 63 and 5. So the 90th percentile would be a score of 69.4 or 69.41. All right, the golf scores for a school team were normally distributed with a mean of 68 and a standard deviation of 3. Find the probability that a golfer scored between a 66 and a 70. So what a picture would look like for that, we have a normal distribution. We have a mean of 68, so 68 would be in the middle. And we want the probability that a golfer scored between 66 and 70. This would be, our lower bound would be 66 and our upper bound would be 70. We are looking for the area, so we are using the normal CDF because we are looking for the area. So I'm going to go to my calculator. I'm going to use my normal CDF. My lower is 66, my upper is 70. It told us in the problem that the mean was 68 and the standard deviation was 3. So the probability that a random golfer scored between 60 and 70 would be 0.4950, or about 50%. (2,000 students took an exam. The scores on the exam have an approximate normal distribution with a mean of 81 and a standard deviation of 15. Calculate the first and third percentiles. Remember that the first and third quartile. The first quartile is the same as the 25th percentile. Remember that percentiles represent the area to the left. So what's that K value such that 25% is less than or equal to it? We are given the area. If we're given the area, we're using inverse norm. Our area in this case is 25% or 0.25. The mean and standard deviation are given to us in the problem. And so we're just using that inverse norm feature on our calculator. The third quartile is the 75th percentile. That just changes the area to 0.75. And remember, both of these have a left tail. All right, B, calculate the middle 50% of the exam scores are between what two values? This again can be done with the inverse norm. We are given the area in between two scores is 50%. So we're given the area, so that's why we use inverse norm. This time the tail is middle because the shading is in between those two values. So if I go to my second distribution, inverse norm, the area was 50%. The mean was 81 and a standard deviation of 15. This time the tail is center, not middle. And it gives us two values here. We have a 70.88 and a 91.12. So the middle 50% of the scores were between 70.9 to 91.9. And again, that was found using that inverse norm. As always, if you have any questions, please reach out. I'm happy to jump on a Zoom or help over email or whatever it may be.